how to construct finite difference approximations. So I'm going to use the same example here. Let's say I want to construct, let me actually use a different example here. I want to construct partial u, partial x. Question mark. All right. How do I approximate this derivative? Of course, I first need some constraints. Okay, I'm saying I want a sparse enough approximation. I want a compact approximation so that my finite difference approximation would only involve the immediate neighbors of the grid points. Of course, you can put other constraints. Let's say I want it to involve only neighbors and neighbors of neighbors. You can do the same thing here, but let's do the simplest demo here. So let's do this as approximate as something times ui plus 1 plus, let's say I'm going to say a here. A is something unknown, plus b times ui plus c times ui minus 1. Okay. And the question is, how should I choose A and B and C so that this is a good approximation? So what quantifies a good approximation? We have only talked about the truncation error here, right? So maybe a good approximation means, like, at least the one aspect of a good approximation means the truncation error should be small. Okay, and we know how to compute the truncation error. So tau is equal to the difference between a ui plus 1 plus b ui plus c ui minus 1 minus partial u partial x. And let's use what? Taylor series to figure out what all of these terms are. This is equal to a times ui, this is b times ui, c times ui, this is nothing, plus a delta x times first derivative at xi, plus c times delta x first derivative, and this is minus first derivative. Minus, because the truncation error is equal to the approximation minus the actual derivative. Oh, yes, it's a minus c. Thank you. Okay, very good. And we want to cancel this, right? I mean, we want to cancel this, of course, and we want to cancel this. And to cancel the first equation, we need a plus b plus c equal to 0. To cancel the second equation, we want a delta x minus c delta x equal to 1, right? Okay, we have two equations, but we have three variables, so we can go further. We can go like plus half of a times delta x squared partial square u partial x squared. We can have plus half of c times delta x squared partial square u partial x squared. We can also put another equation to cancel this. And that means, because both has a delta x squared, so I don't have to worry about that, a plus, I hate that, a plus c equal to 0. Okay, I have three equations to solve. And once I solve these equations, I know the truncation error has to be O delta x cubed, right? Then I'm happy. Okay, that's as good as I can do, right? Because I have three coefficients to play with. I can only enforce three equations. If I want the scheme to be even a higher order, I need to have more terms and have more unknowns, right? Okay, this equation, of course, because we are in numerical methods class, we don't really want to solve that analytically, all right? We can say, okay, we can put a matrix 1, 1, 1 times A, B, C equal to 0. That is actually the first equation. All right. And the second equation is, let's see, we want to, I think it's easier to make it 1 over delta x, so that I have 1, 0 minus 1 times ABC equal to 1 over delta x. And also I have 1, 0, 1 times this equal to 0. All right. So we can see that all the coefficients scales with 1 over delta x. If delta x goes larger, all the coefficients go smaller proportionally. So that we can solve for, we can basically multiply delta x on both sides, so that like this gets to be just 1, and we are actually solving for A delta x, B delta x, C delta x. So we'll just solve this using MATLAB. Construct the matrix 1, 1, 1, 1, 0 minus 1, 1, 0, 1. That's the matrix. Backslash 0, 1, 0. Okay, we get half 0 minus half. What does that mean? That means A delta x equal to half, B equal to 0, C delta x equal to minus half. We plug that into the scheme. That's ui plus 1 minus ui minus 1 divided by 2 delta x. That's known as the central difference scheme for approximating the first derivative. Okay, so for any derivatives or anything, you can approximate it that way. You can construct a scheme for approximating the partial derivatives that way. Any questions? No? Yes? Very good question. That's actually a very insightful question. So the question is like this. If I need a fifth order scheme, depends on what operator I need to approximate, I may need the nearby, let's say 7 points or something like that, right? Let's say I need 7 points. Okay. Then as I move closer and closer to the boundary, I no longer have 3 points on each side, right? Maybe I know if I'm exactly the next point to the boundary, I have only 1 point on the left-hand side. So what do? So there are 2 approaches to deal with this, and also you can combine this. The first approach is to bias your stencil. If I'm right next to the boundary point and I still need 7 points, then I'm going to use 1 point on the left, the current point, and 5 points on my right. And I'm going to derive a different finite difference approximation scheme just for that point. Similarly, I'm going to derive just a different finite difference approximation for the point, for the second point away from the boundary, etc., etc. So that's one way. Another way is to use the boundary condition. Okay, so if I have a boundary condition, let's say the Dirichlet boundary condition or Newman boundary condition, I'm going to talk about that later. So the boundary condition may involve some derivatives. So if you write the finite difference scheme not only as a combination of the value of the function at different grid points, but also plus another term that actually has the boundary condition in it, then you can derive some different scheme that involves that makes use of the boundary condition. That may get you 1 less point than you actually you typically need in the interior. Okay, so these are two ways of dealing with finite difference around the boundary. All right, does that answer your question? Oh, are there forward and backward difference in addition to the central difference? Yes. And both forward and backward difference, I mean, you can see that if I don't require myself to satisfy the third equation, then I only have two equations for three variables. That gives me 1 degree of freedom. And I can use the 1 degree of freedom to say that I want less weight on the left-hand side grid point. I want more weight on the right-hand side grid point, or vice versa. That gives me a biased derivative. These are only first order accurate, but it may have benefit in terms of stability when applied to a particular differential equation. So stability is of the differential equation is what we are going to discuss next. It is not directly linked to a finite difference approximation. It is linked to a combination of a finite difference approximation and the differential equation you are solving. Okay, so let's take maybe 5 minutes break and continue on stability, which is going to require your linear algebra skills.